Hello and welcome to episode 2 of our 3 videos explaining how to teach energy at 14 to 16. If you've not watched the first episode, I suggest you go and watch that before watching this one. What we're going to think about today is the idea of energy in a thermal store and how to teach those concepts at 14 to 16. So what do we need to understand to consider the energy in a thermal store? To answer that question, we have to think about the arrangement of particles in a solid, a liquid and a gas. We know that in a solid, the particles are locked in place and they vibrate. In a liquid, they're able to vibrate, but they can also move around within the structure. And for gas, well, they just fly around with speed. And what happens if we increase the temperature? Well, in a solid, the particles vibrate more. In a liquid, they vibrate more, but they also move around faster. And in a gas, the particles just get to a higher speed and move around more quickly. How do we know it's energy in a thermal store? Well, to answer that, we have to be able to come back and find it later. And the answer is yes, you can. Of course, you can have a hot object and you return to it and it is still hot. The trouble is it's very difficult to keep it hot. How do you increase the energy in the thermal store? Well, as you've heard from episode 1, we have to use a transfer process and the mechanical work, electrical work, conduction when putting it in physical contact with a hotter object, and radiation, the electromagnetic spectrum, probably in the infrared. All of those are processes that will increase the energy in the thermal store. So can you calculate the energy in a thermal store? Well, the answer is yes, you can, but it's very difficult to define zero. And to understand that completely, you need to think about absolute zero, which is talked about at Key Stage 5. At GCSE, we think about the change in the amount of energy in the thermal store and use the formulas to calculate that. Here I've presented the formulas with theta and capital T for temperature, depending on which specification you're using. Notice the triangle, the delta, means change in, both for energy and for the temperature. What this equation shows us is that if you have a larger mass that you're trying to heat up, then the amount of energy needed to increase the temperature will be greater for the larger mass. It also shows us that how much energy is needed to change the temperature will depend on what material you're using. And this brings us to the idea of specific heat capacity. It tells you how much energy will be needed to increase the temperature of 1 kilogram of the material by 1 degree C. Notice that the C in the equation is different for every material that you might choose to use. We can do experiments to work out what the specific heat capacity is, and that's one of the required practicals in most specifications at GCSE. And to do that, we would use the fairly standard cylindrical block of aluminium or brass or steel with the holes drilled in, one to have an electrical heater fitted, and that will be able to measure the amount of energy transferred to the solid. That'll be done either with an ammeter, a voltmeter and a stopwatch, or with a joule meter. And well, to measure the change in temperature, we would use a thermometer, and that fits into the other hole. Let's have a look and see how that experiment works. So this is the apparatus you would use to measure the specific heat capacity. Here's the aluminium block and the top pan balance that you can use to measure the mass. We've locked the heater into the hole by pressing a pin down the side. There's the thermometer to measure the temperature, both in holes drilled into the block. The circuit here will transfer energy electrically. The potential difference is measured with the voltmeter and the current flowing is measured with the ammeter. All of that will increase the temperature of the block. The stopwatch is used to measure the time that the power supply is switched on for. We can just adjust the potential difference in current and we're ready to take our measurements. The initial temperature is measured from the thermometer. Here you can see it's just over 26 degrees C. And we switch it on, starting the stopwatch at the same time. After about 8 minutes, the temperature will have risen enough to do the measurements. We switch off together, allowing a bit of time for the temperature just to stabilise in the block. There we can measure the final temperature as 36 degrees C and use the top pan balance to measure the mass. That will allow us to make the calculations as shown. Notice that the value we've got from doing the experiment is just a little bit higher than the accepted value, but that allows us to discuss and talk about the energy losses to the surroundings. The experiment can be repeated with other materials, allowing a comparison between brass, steel, iron, whatever you've got available. The alternative way of measuring the energy transferred is to use a joule meter. The power supply is connected to one side. The meter will then measure how much energy is transferred through the output stage into the block. Switching it on, you'll see the meter starts to count the joules. Here it's measuring in kilojoules. Makes it simpler than using the current and the voltage from the meters. So just a brief recap. Specific heat capacity tells you how much energy is needed to raise 1 kilogram of material by 1 degree C. Every material has a different value of that, and a higher specific heat capacity means that it's more difficult. It takes more energy to raise the temperature of that object. And the opposite is true as well. If it's got a high specific heat capacity, it will probably stay warmer for longer because there is more energy available to transfer out of the system to cause the temperature to decrease. Now we need to think about what happens at a change of state, and that's how we move to the idea of latent heat. Every time that you change state from a solid to a liquid or a liquid to a gas, you are breaking bonds. They could be van der Waals bonds, they could be ionic bonds, but to do that energy is needed. If you're melting and freezing, then you're going to use the idea of latent heat of fusion. And if you're boiling and condensing, then you're going to use the other version of that, which is the latent heat of vaporisation. Fusion linked with the idea of joining to make a solid, vaporisation changing from a liquid to a gas. When we consider the formulas, now you'll see there is no delta. That's because it's a finite amount of energy that's needed to melt a specific mass of the material. And similarly with the latent heat of vaporisation, it's a certain amount of energy that is needed to boil a certain mass of the material away from the liquid. It's important to state and be sure about the fact that temperature stays the same in the processes of melting and freezing and boiling and condensing, but the energy stored in the material does change. So let's have a think about that in more detail. I'm going to represent two particles bonded together in a solid, so they're in a fixed position. Therefore, they will have a vibrational motion about their fixed positions. If I transfer energy to the system, that vibrational motion will increase, and the energy in the thermal store would increase, and therefore the temperature increases. And that's linked with the idea of specific heat capacity. If I transfer energy to the system and it breaks the bond, energy stored in the material is still increased, but the temperature stays constant. And that's the idea of latent heat. We can do experiments to try and calculate or to measure the latent heat of fusion, latent heat of vaporisation. And to do that, one of the easy ways to do that is to take a mini kettle and to fill it with crushed ice and then measure the amount of energy transferred to the ice electrically, and then to measure how much water is melted from the ice. Let's have a look and see how that experiment is done. So this is the apparatus you would use to measure the latent heat of fusion of ice. We use a mini kettle and a power meter with the stopwatch to measure the energy transferred electrically, and the top pan balance will allow us to measure the mass of water. Adding the crushed ice into the mini kettle, when we switch it on, it will start to melt the ice, with the stop clock being used to measure 30 seconds, which will be enough time to get the water to measure. Pouring the water into the jug allows us to measure the mass of water. Here we get about 40 grams, and this can then be put into the equation to measure the latent heat of fusion. Notice the value we get here is slightly greater than the accepted value, again leading to a chance to discuss the uncertainties in the experiment. Using a similar setup, it's also possible to measure the latent heat of vaporisation. And again, using the mini kettle, this time allowing it to boil, you can measure the mass of water that evaporates and use that to calculate the latent heat of vaporisation. Let's have a look at that experiment. This is the apparatus you can use to measure the latent heat of vaporisation of water. we place a mini kettle on top of a top pan balance with the lid removed so that it continues to boil. If you reset the top pan balance at the same time as starting the stopwatch, water will boil away from the surface of the water in the kettle and the value on the top pan balance will decrease. After about 1 minute, 75 grams of water has boiled off from the surface of the water, and this value can be used to calculate the latent heat of vaporisation using the equation. One of the nice things about doing those two experiments is it allows you to compare the latent heat of fusion and of vaporisation for the same material, and to compare and show that breaking the bonds in different ways from solid to liquid and liquid to gas requires a different amount of energy. And then it's not too difficult to extend that and say that therefore it's different for different materials as well. One final idea it's worth considering is the idea of what the temperature time graph looks like from when you go from a solid all the way up to a gas. So on the left hand side here we've got the temperature which is in freezing. I'm going to consider this to be ice, with the axis being 0 degrees C. So as we move to the x-axis, that's where the ice will melt at 0 degrees C, and that will go all the way up until it boils at 100 degrees C. And then I've extended the graph up where it's possible to make the gas hotter than 100 degrees C. It'll need to be pressurized in some way, but let's just consider where the specific heat capacity and the latent heat fit into this graph. So when you're below the melting point, that's when you've got your specific heat capacity of ice, which will mean you need a certain amount of energy to raise the temperature. That will continue with the liquid, where you've got a different specific heat capacity, and energy will again be needed to increase the temperature of the liquid up until it boils. And when you get past the boiling point, the specific heat capacity, it still has a value, and it'll be a different value, and you'll still need energy to raise the temperature further. At melting, where the temperature is constant, that's where the energy is now going to break bonds, and as the bonds are broken, the temperature stays constant. Similarly, up here at the boiling point, the temperature stays constant and the energy is now breaking bonds. So the temperature increases, energy is required to do that, and the thermal store is increasing. But notice at the melting and boiling points, the temperature stays the same. And it's worth saying, just making it even clearer, that at the different parts of that graph, the values of the specific heat capacity and latent heat are different for each part. They don't have the same value. Decreasing temperature, well, very similar shaped graph. This time we're going to be coming backwards down through that, and we're going to start at a very high temperature and allow it to cool. Energy is taken out of the system, and as it condenses, the latent heat now is transferred from the material, and then it continues down as it cools in the liquid phase, specific heat capacity again, down until it freezes. At that point the temperature stays constant again, and then you can continue to reduce the temperature of the solid. Now that does give a little indication of why you have to be so careful when you're working with steam and steam condensing, because energy is transferred from the thermal store when a gas turns into a liquid, and that can then contribute to the burns, making steam burns significantly worse than scalding from hot water. So in summary, what we've been thinking about in this video is how energy is stored thermally and the ideas and context for that at 14 to 16. Firstly, how that involves the particles and their motion inside the material. Then we thought about how the specific heat capacity determines how much energy is needed to increase the temperature of a solid, liquid and gas. And we also thought about changes of state and the involved latent heat. Thank you for watching. If you would like to see some extension experiments that you can also use in this topic, please continue watching. If you want to use a mini kettle to measure the specific heat capacity of water, you can do that in the following experiment. This is a way of measuring the specific heat capacity of water using a mini kettle. A power meter will allow you to measure the power being transferred to the kettle. Here it's 635 watts. If you add a known mass of water, here it's 358.9 grams, into the kettle, when you plug it in, a stop clock can be used to measure the time it takes and after 1 minute you can measure the temperature rise of the known mass of water. That will allow you to calculate the specific heat capacity. To produce the temperature time graph talked about in the video, you can use a data logger. This first experiment shows you how to produce the part of the graph for melting. To produce a temperature time graph for melting ice, you need to pre-prepare a measuring cylinder of ice with a temperature probe inside it. Connecting this to the computer, you'll see that the temperature inside the measuring cylinder is at -14 degrees C from the freezer. Put that into the water in the jug, and the temperature of the ice will start to rise following specific heat capacity. It continues to rise until it reaches 0 degrees C. Here the -0.4 is the calibration of the data logger, and it will remain at this even though the water in the jug is brought up to 40 degrees. That carries on until all of the ice melts, and at which point the temperature will start to increase again, and then this is the specific heat capacity of the water in the measuring cylinder. To continue the temperature time graph for boiling, you can use this experiment. In order to produce the temperature time graph for boiling, we need to use ethanol in a test tube with a temperature probe and use a water bath at about 90 degrees C with a temperature probe as well. Connecting that to the computer will allow the temperature versus time graph to be displayed real time. Starting the data logger, we can lift the ethanol into the water bath, and immediately the temperature will start to rise on the computer. Looking into the top of the water bath, you can see the ethanol in the test tube next to the data probes. As the temperature approaches 80 degrees C, it starts to level off until at 80 degrees it remains constant, because that's where the ethanol is boiling. Again, looking into the water bath, you can see the bubbles in the ethanol within the test tube in the water bath. The graph then shows quite clearly how the temperature remains constant as the liquid boils.